You're going to want to rewatch this several times, I'm telling you. Not so much because of my excellence, but because of the excellence that is physics. So, anyway, what we're learning today is it's the backbone, it's the foundation, it's the fundamental stuff that we're going to use to really start studying motion. It turns out that if you go back to Newtonian mechanics, Isaac Newton's physics, right, in the late 1600s, 1680, I believe, but don't quote me on that. He published his big works, and the revolution with all that was, he said, if you know the conditions on an object, you know what it's going to do for eternity. It was called deterministic physics, right? You can figure out, if I know where something is and how fast it's moving and what its acceleration is, I know everything about it for the rest of eternity. Right? Pretty powerful ideas. And it turns out that in the early to mid-1900s, quantum physics came along and said, well, that's not entirely true. And throughout stuff like uncertainty and chaos theory gets in there and makes for some interesting exceptions. But there's a reason why it took us 200 years to figure out that Newton wasn't quite right about that determinism. Right? Because for basically everything that we're ever going to see in our lives, we do know everything. If we know the initial conditions, we can find out what's going to happen for the rest of it. So the stuff that I'm showing you here is enough to build airplanes and send humans to the moon and bring them back. The physics that we're doing here is pretty powerful. So let's take a look at it. All right, and we're going to start by realizing that these should be your tattoos. All right, so your homework assignment tonight is to go to your favorite local tattoo shop. And right next to the avocado, I want you to get these two equations that I'm going to give you today tattooed in prominence. The best option is to put it right here on your forearm, probably on the left forearm so that you can just always look down at it. You can do it there. If you're a big fan of the selfie, any of you guys take a lot of selfies, do a lot of Snapchatting, you can put it across your forehead. That way in every picture you've got the equation. Make sure you do it backwards so that you can read it in the picture. All right. Be a good look. Regardless, it must be made permanent on your body somehow so that even when you're old and wrinkly, you look down and, oh, yes, I remember that. It'll be good. So, let us begin. Your new tattoos. This is exciting. What I'm showing you works for all motion, as long as you have constant acceleration, which in the world we usually do. Or we can at least break it down to some time that we do. The old stuff, what we've been doing, still true. Right? It's not like I told you something that wasn't quite true. It is still true. It's just not always the most useful or the easiest way to solve problems. There's a more general way. It's kind of like when you first, in Algebra 2, when you first look at quadratics. First you factor them. And then you learn, well, some of them factoring doesn't work that well. So now we're going to teach you the quadratic formula, right? I'm showing you the quadratic formula of motion problems, if you will. And I want to start with an aircraft carrier. Because I think this is a way to build these equations where it will actually make sense. And they should. There's an element of common sense to them. So remember what we're trying to do. Given the initial conditions, we're trying to figure out where something will be at any time down the road. All right? So for this example, I'm going to build a base right here. Let's call this base Pearl Harbor. Because then we get to be in Hawaii, which is nice. And it's right next to the ocean. And then out in the ocean, we've got an aircraft carrier. Big old aircraft carrier. Right, there's the water around it. Don't laugh at me. And on the aircraft carrier, we've got an aircraft that can take off from the deck. And it's going to accelerate as it does. So, basically what we're trying to do is we're going to try and come up with an equation that tells us how far the aircraft is from the base at all times. All right? Now realize, this is just one example. The equation that we come up will work for anything. Right? So that's why I'm trying to kind of come about it in this concrete sort of way so that it maybe actually makes a little bit of sense. There's three things that I need to worry about. three kind of factors that come into play here. The first one is pretty common sense. How far apart do they start? Right? Do you see how that's gonna come into play, right? How far from the base are you when the clock starts? And we're going to call that our initial position, which gets this little subscripted 0. We call it x aught. Fancy word for 0, right? But it means how far are you when time starts. So that's this distance right here. That's one thing you'd need to know if you were going to figure out how far away they were. You got to know how far you started, right? Another thing that you got to know is you got to know how fast the aircraft carrier was moving when the plane took off. Right? So we're going to call that V-aught, the initial velocity. And then the last thing that we're going to worry about, what else do we need to know? How fast is the plane accelerating off of that aircraft carrier? So that's the last one. So we also need to know what is the acceleration. If you know those three things, you know it all forever. Haha. So let's do that. Let's try to build the equation. It looks like this. First of all, and let me be clear about this, because this is something we always have to do when we do motion problems. I'm going to say the base is my reference point. In math, you call this the origin, right? It's where the two axes cross. This is our reference point or our origin. And I'm going to define anything going to the right is my positive x direction. Anything going to the left is negative. Right? That's going to be really important. So now let's build that equation, all right? Looks like this. X, and I'm going to do function notation. You guys cool with function notation? X as a function of time. Just makes it really clear that the position depends on time. Depends on three things. All right, well, the simplest one is I've got to start off, this whole equation needs to start this distance from where I began, right? So I'm going to start off by saying my position is equal to wherever I started. And now I just have to factor some stuff in. Let's factor in the constant velocity of the aircraft carrier. How would I do that? If I know that the aircraft carrier is going to be moving, what's an equation that tells me the distance it's traveled over time? We can do that, right? Remember that one? Distance is the average velocity times the time. Is the velocity of the carrier changing? It's constant, right? It's just going to move through the water. The acceleration comes from the plane. So instead of the average, what are we calling it? We're calling it the initial velocity, right? Does that make sense? No? Yeah? 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 Yeah. All right. So now, this is all good. Now we just need to figure out how do we account for the distance covered by this accelerating object. And the nice thing is, we already know this equation right here tells us where the aircraft carrier is going to be, doesn't it? So we just need to add in how far ahead of the aircraft carrier is the plane. Does that make sense? We're just trying to figure out how far ahead of the carrier is the plane. So what that means is we can imagine that this is sitting still, right? That now just for a moment, let's pretend that our reference point is sitting right here. We're just trying to find where the plane is after it accelerates. And for that, I think I need to do just a little bit of side work to get us to the answer. But follow this. It's not too bad. It's actually doing exactly what we've been doing in this chapter. If I know the acceleration, then all I need to do is I need to start with this equation where the distance traveled from the accelerator is the average velocity times the time. How do I find the average velocity for the airplane compared to the aircraft carrier? Average velocity, remember, is 1/2 the final velocity plus the initial velocity, right? This is the average velocity. That's an equation that we have, and then I'm just going to leave the time up there because it was already there. Now, remember I said we can compare it to the aircraft carrier. What's the initial velocity compared to the aircraft carrier? When you're sitting on the deck of the aircraft carrier about to take off, what's your initial velocity compared to it? It's 0, right? Compared to the carrier, you're not moving at all. So this goes bye-bye. So now we can simplify this, and it's just going to be 1/2 the final velocity times the time. Do we know yet? We don't know yet what the final velocity is, right? But if we know the acceleration, we can find it. Right? Because remember that the change in velocity is equal to the acceleration times the time? Right? I mean, that's what acceleration is. If you're accelerating at 9.8 or 10 meters per second, then after 1 second you're going 10, after 2 seconds you're going 20, 3 seconds you're going 30, right? So the velocity is just acceleration times the time. All I'm going to do is I'm going to go whoop, and I'm going to put that in here for my final velocity. So remember this was an equation for distance. I've got distance is equal to this 1/2 times AT, because AT is my final velocity, times t. Can I do one more set of algebra here? And distance is equal to 1/2 AT squared. Is that cool? And so without integration, I just found the distance of an accelerating object. Those of you guys who may have had calculus, that's kind of cool to see. So there it is. Anybody got chills right now? It's okay, you don't have to tell me. It'll be our little secret. This right here, though, this is, for most of you guys, the first tattoo of your life. Congratulations. Even if it's not the first, it's definitely the best. Write that down, put boxes around it. Of course, I'm kidding about the tattoos. But I'm not kidding when I say that this may be the most important equation we do all year. If you only remember one equation this year, you can make a good argument that this is it. We're going to use the heck out of it for the first 2 chapters, and then it'll keep coming back around afterwards, because it tells us the position of any object over time. Right, as long as we know the initial conditions, where it starts, how fast it started moving, and what the acceleration is. All right. Quickly, let's look at, I told you there were 2 equations today. This equation has a little brother. Whoops. If you're a calculus folk, you could take the derivative of this equation. Don't look too excited. If you're not a calculus folk, you can still come up with the little brother equation just by thinking about it. So what we want, the first one was an equation for the velocity, or I'm sorry, for the position. Tells us where it is. This one is going to tell us the speed. So if I want to know how fast something's moving, I need to know 2 things. Can you tell me one of them? What's one of them, Josh? Time will be a factor. This is going to be a function of t. That's good. What else do you need to know? Yeah, it looks like a banana. That's big, right? You got to know the acceleration. In fact, you multiply acceleration times the time, that tells you how much your speed increased or decreased, right? Anything else? You. Distance doesn't matter for velocity. Does that matter? How fast you started? Yeah, sure that matters. So this can be like the, I don't know, use it for like the decoration or the garnishing on your tattoo. This is good. We'll use it. It makes sense though, right? How fast you're moving is equal to the speed you started plus whatever the change is. And so there we go. Those two equations are basically going to be, well, there's a lot in them. Right? Enough that we can cram easily the next 5 or 6 weeks of this class into those equations. And have lots of fun doing it. So that's it. We're going to practice those today. The one thing I want to be clear of, because I've skipped over this in the past, is when we use these equations to solve problems, this one and the Big Brother equation, we've got to be really careful to specify axis and origin. We've got to say, what are we comparing it to? What's our reference point? And what direction is positive? Because if we don't do that, we make silly mistakes. Right? By far the most common mistakes come from not choosing an origin and not choosing an axis or saying which direction is positive. So this slide is just going to practice that. All right? Now, in general, and this isn't always true, in general, usually we say that up is positive and down is negative. Right? You could do it the other way, but it just makes sense, right? You think about math class, because math is where you learn the stuff that we use in here. In math class, that's usually how it works, right? If you were to draw your y-axis, it would look weird if somebody said, this is the positive y direction, right? Up is always positive, plus y. And it would look weird if somebody said, this is the positive x direction, right? There are times in here when we'll do that, because it makes the math easier. But usually, we're going to say up is positive and either forward or to the right is positive. Now, know this. This causes confusion too, but there's not much we can do about it. If I solve a problem using up as positive, and you solve the same problem using down as positive, we'll get the same answer, as long as we're both consistent the whole time. So do whatever you want. Sometimes one makes the calculations easier than the others. All right. Let's practice this, guys, because I've been talking a lot, trying to get you to the exciting stuff. I want you guys to try these first three. So here's a rocket blasting off, right? Just left the launch pad and it's taken off up in the air. Here is Serena Williams tossing up a tennis ball. This ball just left her hand, right? She's tossing it up. It just left her hand. She's going to smack it. And here's some poor fool about to die. I'd like you guys to go through and tell me, for the acceleration and for the velocity, positive or negative. There's no zeros up here. So remember we did this with graphs? We looked at graphs and we tried to decide positive or negative acceleration, positive or negative velocity. Do this for the pictures right now, please. Do it by yourselves and then we'll talk about it in 1 or 2 minutes. Go.